National Electrical Code 250.148d addresses the splicing of equipment grounding conductors. This section states that where equipment grounding conductors of different sizes are spliced together, the splice shall be made with a splicing device approved for the purpose and for the largest conductor involved. This means that all equipment grounding conductors, regardless of their size or the circuit they serve, must be connected at a single point using a splicing method that is listed for the intended use. The connector used for the splice must be rated for the largest equipment grounding conductor present in that connection. In practical application, if you're working with a combination of 13 amp and 20 amp circuits using non-metallic cable, you'll encounter both 14 American wire gauge and 12 American wire gauge equipment grounding conductors. According to the National Electrical Code, all of these equipment grounding conductors must be spliced together within the electrical box. It is crucial to use a connector or splicing method that is not only approved for grounding purposes but also rated to accommodate the largest conductor, which in this case would be the 12 American wire gauge equipment grounding conductor. The fundamental principle behind grounding is to create a low impedance path that allows fault current to safely return to the source, which is usually the service panel. By ensuring that all equipment grounding conductors are properly spliced together, you establish a continuous and reliable path for fault current. This is regardless of which circuit or device experiences the fault. A continuous path allows the overcurrent protection device, such as a circuit breaker, to quickly detect the fault and interrupt the circuit. This minimizes the risk of electrical shock or fire. It's important to understand that the size of the equipment grounding conductor isn't determined by the size of the device it's grounding, but rather by the rating of the overcurrent protection device protecting the circuit. For instance, if you have a 20 amp circuit, the equipment grounding conductor must be sized according to the requirements for a 20 amp circuit, even if the device connected to that circuit only draws a few amps. This means that in some situations, the equipment grounding conductor might be larger than the circuit conductors feeding the device. Let's delve deeper into the specifics of equipment grounding conductors and their role in electrical safety. The equipment grounding conductor, often referred to as the EGC, is a critical component of any electrical system. Its primary function is to provide a low impedance path for fault current to flow back to the source, allowing the overcurrent protection device to quickly trip and interrupt the circuit in the event of a ground fault. Without a properly sized and installed equipment grounding conductor, fault current could flow through unintended paths, such as metal enclosures or equipment, creating a dangerous shock hazard. The National Electrical Code provides detailed requirements for the sizing, installation, and splicing of equipment grounding conductors. These requirements are designed to ensure that the equipment grounding conductor can safely carry the maximum available fault current without overheating or causing a fire. One of the key considerations when working with equipment grounding conductors is the type of wiring method used. For example, non-metallic cable typically includes an uninsulated equipment grounding conductor that runs alongside the insulated circuit conductors. In contrast, metallic conduit systems themselves can serve as the equipment grounding conductor, provided that they are properly installed and maintain electrical continuity. When splicing equipment grounding conductors, it's essential to use connectors or splicing methods that are specifically listed and labeled for grounding purposes. These connectors are designed to provide a reliable, low-resistance connection that can withstand the stresses of normal use in fault conditions. Common splicing methods for equipment grounding conductors include the use of crimp connectors, split-bolt connectors, and grounding screws. Regardless of the method used, it's important to ensure that the connection is mechanically secure and electrically sound. Now let's discuss some common scenarios where the splicing of equipment grounding conductors is required. One common scenario is in electrical boxes where multiple circuits are present. In these cases, all of the equipment grounding conductors from each circuit must be spliced together to create a common grounding point. This ensures that all metal enclosures and equipment within the box are effectively grounded. Another scenario where splicing is required is when extending or modifying existing circuits. When adding new outlets or fixtures to an existing circuit, it's necessary to splice the equipment grounding conductor from the new wire into the existing equipment grounding conductor. This maintains the integrity of the grounding system and ensures that the new equipment is properly grounded. In addition to the general requirements for splicing equipment grounding conductors, the National Electrical Code also provides specific rules for certain types of equipment and installations. For example, there are special requirements for grounding equipment in hazardous locations, such as gasoline dispensing facilities or chemical plants. These requirements are designed to minimize the risk of explosion or fire in these potentially dangerous environments. It's also important to note that the National Electrical Code prohibits the use of certain types of connectors and splicing methods for equipment grounding conductors. For example, wire nuts are generally not permitted for splicing equipment grounding conductors, as they may not provide a reliable, low-resistance connection. Instead, the listed and labeled grounding connectors should be used. When working with equipment grounding conductors, it's always a good idea to consult the National Electrical Code and other relevant standards to ensure that you are following the proper procedures. Additionally, it's important to have a thorough understanding of the principles of grounding and bonding, as these concepts are essential for ensuring electrical safety. Grounding refers to the connection of electrical equipment and systems to the earth, while bonding refers to the connection of metal parts to create a continuous electrical path. Both grounding and bonding play a critical role in minimizing the risk of electrical shock and fire. In summary, the splicing of equipment grounding conductors is a critical aspect of electrical safety. By following the requirements of the National Electrical Code and using proper splicing methods, you can ensure that equipment grounding conductors are properly installed and that electrical systems are safe and reliable. Remember that the equipment grounding conductor size is based on the overcurrent protection device, and to use the proper splicing methods for all of the equipment grounding conductors. When dealing with various sizes of equipment grounding conductors, the National Electrical Code 250.148D provides explicit guidance to ensure electrical safety and proper functioning of the grounding system. Here's a breakdown of key considerations. First and foremost, the code mandates that when equipment grounding conductors of different sizes are spliced together, the splicing must be accomplished using a device that is specifically approved for this purpose. This seemingly simple requirement is paramount because not all splicing devices are created equal. Only those that have been rigorously tested and certified for grounding applications can guarantee a reliable and low-impedance connection, essential for directing fault current safely back to the source. Secondly, the splicing device must be appropriately sized for the largest conductor involved in the splice. This stipulation addresses the physics of current flow. A larger conductor can carry more current than a smaller one, and the splicing device must be capable of handling the maximum potential fault current that the largest conductor might carry. If the splicing device is undersized, it could overheat, melt, or even fail catastrophically under a fault condition, defeating the purpose of the grounding system. Thirdly, it's crucial to understand the reasoning behind this requirement. The primary purpose of the equipment grounding conductor is to provide a low impedance path for fault current. This low impedance path ensures that in the event of a fault, a large amount of current will flow quickly back to the source, tripping the overcurrent protection device, such as a circuit breaker or fuse. This rapid tripping action minimizes the duration of the fault, reducing the risk of electrical shock, fire, and equipment damage. Fourthly, when different sizes of equipment grounding conductors are connected together without a properly sized and approved splicing device, the connection may not be able to handle the fault current adequately. This can lead to a higher impedance path, slowing down the tripping of the overcurrent protection device and increasing the potential for hazardous conditions. Fifthly, consider a practical example. Suppose an electrical box contains both a 15-amp circuit with a 14 American wire gauge equipment grounding conductor and a 20-amp circuit with a 12 American wire gauge equipment grounding conductor. According to National Electrical Code 250.148D, these equipment grounding conductors must be spliced together using a splicing device that is listed for grounding and rated for at least a 12 American wire gauge conductor. A common mistake is to use a wire nut which is not listed for grounding applications, or a wire nut that is too small for the combined conductors. Sixthly, the code doesn't specify the exact type of splicing device that must be used, but it does require that it be approved for the purpose. This means that the device must be listed by a recognized testing laboratory such as underwriters' laboratories or electrical testing laboratories, and must be marked with its intended use and conductor size range. Common types of approved splicing devices for grounding conductors include crimp connectors, split bolt connectors, and grounding bus bars. Seventhly, installation of the splicing device is also critical. The conductors must be properly stripped, cleaned, and inserted into the connector. The connector must be securely tightened or crimped to ensure a reliable connection. It's also important to follow the manufacturer's instructions for the specific splicing device being used. Eighthly, regular inspection and maintenance of electrical systems are essential to ensure the continued effectiveness of the grounding system. Connections can loosen over time due to vibration, temperature changes, or corrosion. Therefore, it's important to periodically inspect all grounding connections, including splices, and tighten or replace them as needed. Ninthly, one must avoid a common misconception. It is that the size of the equipment grounding conductor is determined by the size of the load connected to the circuit. As mentioned earlier, the size of the equipment grounding conductor is determined by the rating of the overcurrent protection device protecting the circuit. This means that even if a circuit is only supplying a small load, such as a lamp, the equipment grounding conductor must still be sized according to the overcurrent protection device. Tenthly, when in doubt, it's always best to consult with a qualified electrician or electrical engineer. These professionals have the knowledge and experience to ensure that electrical systems are installed and maintained in accordance with the National Electrical Code and other applicable standards. They can also help to identify and correct any potential hazards or code violations.